thank you very much for the invitation, and to Sam and Laszlo also. And so I'm very happy to be here for this birthday conference. And what I'm going to talk about today is local regularity for the Landau-Coulomb equation. Okay, so this is very much related to Maria's talk. But first, let me just say how I met Alexis. Just 2 minutes. So I was in Marseille. I just finished my PhD, and I was working on scalar conservation laws. Okay, so I was so during my PhD, I mostly studied Hamilton-Jacobi equation with convex analysis techniques, and I was eager for new problems. So I was in the team by Cyril Galouette, and he asked about the following problem. So you consider a scalar conservation law in a multidimensional domain, okay? And you have a boundary condition. Okay, so you have the BLN condition for that, but you also have the nice entropy solutions that were defined in 1997 by Felix Otto. Okay, and we were asking ourselves the question of what happens if you do the parabolic approximation? Can you do something between those two quantities? Okay, so Cyril Galouette asked about this question, and I was working with Julien Vauven. Okay, and in order to solve this problem, so it took us a while, but in order to solve this problem, another guy came into the game. And so I was learning new things about scalar conservation laws, reading Denis' book from first page to last page. Okay, so I had a very good time. And so, but okay, I needed some information about what happens close to the boundary. And so I had to read many papers by Alexis. So, I was a PhD student. I never met Alexis. And I said to Cyril Galouette, I need those results about Alexis Vasseur. And he told me, he's in my office. Okay, so I was very impressed. So Thierry told me, yeah, you should come and meet Alexis. And then he explained me some results about strong traces for scalar conservation laws. So, okay, so I can give you at the end, the answer is that you can bound this like epsilon to the 1/3. And you should think about it as if you have no boundary, it's epsilon to the 1/2. Is it optimal? I don't know. I still don't know. I did not check the literature. I just came up with this small story 5 minutes ago. So perhaps now it is known that you can do better than that. Okay, I don't know. And then after that, I did not. I moved to other topics, and I think the next time I met Alexis is when I visited Austin. Okay, so it was at the time, I think when I saw you, it was temporary, and it became more and more permanent. Okay, and at that time, we discussed mathematics, among other things. And you told me how enthusiastic you were about the De Giorgi methods. And at that time, so it was like in 2006, I think something like that. Okay, and yeah, it sounds. I was. It looked interesting, but okay, I forgot about it. And then, like 10 years later, with Clément Moureau, we started looking at. I started much earlier. I started in 2011, but then something happened in 2015, and we started to study kinetic equations, Fokker-Planck equations, and we tried very hard to do the Krylov-Safonov approach to this problem, and we failed, and we failed, and we failed. At some point, we tried the Georgie, and it worked. And then we realized that François and Alexis was doing exactly the same. And and this is where I started interacting more with Alexis. So let me. I won't tell you anymore. Yeah, I think this is interesting because this has to do with scalar conservation laws, and the rest of my talk is not concerned with scalar conservation laws, since I also consider the Landau-Coulomb equation. Okay, so perhaps let me. You have a small break when during my. I will try to erase the blackboard with this. I cannot speak when I erase. I'm sorry. Okay, so Maria already told us about this equation. That's why I had time to tell you this small story, because she gave all the references and everything, and that's very good for my talk. I can dive into details, technical details that you're gonna love. Okay, so the equation is written this way. Okay, so this is a matrix. I remember. The diffusion matrix. And as Maria explained to us, this function is, so I change a little bit the notation. Okay, it's the convolution with another matrix valued function. Okay, so you can write it. And this small a is this, so the projection, yeah, I can call it P of Z also, 1 or 8 by Z. Okay? So what I would like to explain today is the following results. So you have also an initial condition. Okay? And as Maria explained, you have conservation of mass and energy, and you have the decrease of entropy, right? So you know that this quantity is conserved. So you assume that this is initially finite. So everything is non-negative, right? So this is the mass. And you also have the energy. That is conserved. So you assume that the energy and initial mass are finite. And you also have that the entropy decreases. Okay, so I will come back to that later. We will discuss about this positive term. Okay, so you also have to assume that this quantity is finite. Okay, and it bounds the integral of f log f dv for any time t. Okay, so the result is the following. Yes, so it's with François Gols, Alexis, So you can so assume well, those three conditions: mass, energy, and entropy bounded, finite, and consider a solution of the Landau equation, Landau-Coulomb. Okay, so let me call this Landau-Coulomb. So a solution that is symmetric. So what does it mean? It means that it looks like this. Okay, it has a symmetry with respect to a given axis. Okay, then let me call U the solution. Then U is smooth away from the axis. Okay, so this is the result I would like to discuss in the remainder of this talk. And there is a nice corollary, pretty completely straightforward. If you assume this and U radially symmetric, then U is smooth away from the origin. Okay, so this is the kind of things that I would like to discuss today. Okay, I can continue over there. So indeed, I can, even if Maria already told it, perhaps I should discuss one more time the ellipticity of the equation. So do I give an outline of my talk? This would be better, right? To get organized. Let me try. I don't know if I will be able to finish, but so what I would like, I plan to talk about the Landau equation, but Maria did everything. So, I mean, you have the background, I think. And I will basically remind, I will recall some facts that will be used, but we already heard a lot about it. And then I would like to talk about local truncated entropy inequality estimates. So that's the technical part, and we will try to go slowly into it. Okay, and thanks to that, we can prove. I can state the De Giorgi lemma. That is enough to prove smoothness. Okay, in the axisymmetric case. So I will explain in the last part how you use axisymmetry. But in the first sections part, we won't use the axisymmetry condition. So yeah, you have the diffusion matrix, right? We wrote it here. So as Maria said, this quantity behaves nicely from below. Okay, so it's all the eigenvalues So it's inequality between symmetric matrices. All the eigenvalues are bounded from below. Okay, it degenerates at infinity, but that's not a big deal because we want to get local estimates. So we don't care about the fact that it degenerates. Okay, so the method we use here are not global at all. We don't integrate on the whole space a nice decreasing quantity. We want to localize things. So that's why there is local in the title of the talk, and there is local in the second part. Okay, so it enjoys a good ellipticity, but if you look from above, so you can get rid, as Maria did several times, you can get rid of the projection matrix. And then what you can obtain here is 1 over V and SW. So there is 8 pi of F of TW dW. Okay, so you can, so this is the convolution with this guy. But you can also think of it as this quantity, okay? And it turns out that with the estimates you have, you cannot bound. This is not an L infinity function. So as Maria told me several times, this could be, okay, this should be useful, right? But it is not in L infinity. So you have a diffusion matrix that have very, the eigenvalues can be very large, okay? And notice that, for instance, that it is in L infinity if F is in this space with P greater than 3 hat. So it explains why this assumption is natural, right? If you're able to prove that your L infinity LP with P greater than 3 hat, this guy is bounded. So now it's much easier. You have a bounded diffusion. I mean, there is still a lot of work, but still that's a good starting point. So
what about the axisymmetric case? Don't you get bounded away from the axial symmetry?
Yes, no. You are spoiling my talk. It's okay. He said it. Let's do it. In the axisymmetric case, is bounded away from the axis. I'm not going to do the computation because I don't want to dive too quickly into technicalities. But indeed, in this is one of the ingredients in the proof. Now I want to say more because that's a nice computation about the dissipation of entropy. Where do I do that? Perhaps I'm going to do it. No, yeah, I'm going to do it here. Okay. So how do I do that? So I want to compute in general how a quantity like this evolved. So you see, this is a formal computation. I take an arbitrary constant h, and I see what happens. Okay, so yeah, the shadow, I need to go a little bit lower. So I've got divergence, of A grad VF minus divergence of AF, okay, H prime of F. Now I integrate by part. So I've got A grad VF minus divergence of A F, and then here I've got H second of F grad VF. Okay? So now I need to make appear integrals in W. Up to this point, I hide it into this convolution product, okay? But now I need to be more to do that. So I've got the integral of V, the integral of W. I've got the E minus A of V minus W, this guy. Okay, I can forget about the time variable. So I've got F of W coming from here. Then I've got grad VF of V. And then for the other one, I've got F of V grad F of W. And here I've got grad VF of V and the factor here, which is H second of F at V. Okay. I want to make, you see, this is supposed to be positive, right? So I want to get something positive. It does not look very positive to me up to now, but it is. But why is it? So you can continue by factorizing the F's. And then what do you have here? You've got grad VF over F minus grad WF over F. And then you've got this guy, H second of F grad VF at V grad VF of V. But remember, this guy is symmetric. Yeah. There is an obstacle problem. I can. If I move the office, this is going to be bad. Yes, but yeah. So you have to remember the first. It becomes tricky, but okay. Let's. Can you read? Jan? No, more or less. Yeah, I see sim. Yeah. Now you see sim. Okay. So this guy is symmetric, and so what we can do now? So I can continue there on this part. The first choice you can do is H secant of R simply equals 1 over R. Okay? So this boils down to the entropy. H of R equals R log R, for instance. And when you do that, okay, what you obtain is d over dt of the integral of h of f equals minus, I symmetrize, so I take 1/2 a of v minus w f of v f of w grad vf over f minus grad wf over f square. So I should emphasize the minus here. And you see that this is a non-negative symmetric matrices. So all this thing is non-negative. So this is the entropy dissipation. Okay, and Maria mentioned before that De Villette in 2015 came up with a very nice lower bound for this quantity, but I'm not going to discuss it right now. Now we see that the entropy decreases. Okay, but as Maria said also, the only thing you need to do is to prove that F is, okay, she gave an even weaker condition, but if F is an infinity, then F is smooth. So the only thing we want to do is to, so locally, the only thing we need is to be able to prove that locally the function is smooth. Okay, it has to do with parabolic regularity. And so that's why you can, in order to prove that F is smooth, you can use the Georgi techniques. So for classical de Georgi method. So it applies, for instance, for an equation. That's another matrix. Okay, and it is based on L2 estimates. Okay, so basically the kind of things you do is that you truncate U at a level kappa, and you see what happens in a ball of radius r. Okay, and the trick is to prove that this is going to converge to 0 along a subsequence. Okay, so you truncate your solution in order to prove that it's going to be bounded. Okay, we would like to do that here too. We'd like to truncate. So this is the second choice that we did with, to mention Maria here. The second choice you can take is h seconds of r equals 1 over r, but you truncate for the r greater than kappa. Okay, so if you have just a small picture somewhere, where can I do my small picture?
You have a fourth board.
Yeah, and then I will forget about it. No, it will be hidden afterwards. But so if you consider the convex function that is positive and vanishes at 1, okay, this is you can get something like that. Okay, h of f. This is f log f minus 1, but you truncate at f greater than 1. No, first you don't truncate, sorry. So this is this quantity, and basically, when you truncate, you take only this part. Okay, so this is the second choice with kappa equals 1. Okay, this is your second choice. So by doing so, you take the indicator function of f greater than 1. Okay, so this is how it looks. So we go back to the computation that, yeah, I can just write this here. So I have this, and now I make a new choice for this quantity. So now I've got f of v, f of w, then I've got grad f over f minus grad of w. And now I also have grad vf over f as like before, but now I've got an indicator function of f greater than 1. F greater than kappa. Okay? But okay, so you can easily put this one here too. This is in the shadow, so you don't see it. Here you can also put indicator function of f greater than kappa. Okay? And you would like to symmetrize like before. You would like, but you don't have what you need here. Okay? So here you split f of w like f of w indicator of f greater than kappa. And what remains? Almost. I almost made a mistake. So what I'm going to do, the gradient doesn't see constant. I make f of w minus kappa plus the positive part of f minus kappa plus the minimum of w and kappa. Okay? So let me write this in the error term in green. So now, if you do that, you do have by symmetrization minus 1/2 a minus dw f of v fw grad f over f indicator function of f greater than kappa in v minus the same thing in w square. You can symmetrize again, and this is again something which is positive, but you need to pay, you need to take care of the green one. So I compute it. What is the error term? So there is 1 minus 2 minus plus the integral of e minus v minus w. This is this guy. The f of v cancels with the f of v. So it disappears, this one with this one. The f of w disappears with the f of w. And then you've got the gradient in w of f min kappa. And the gradient, so here I can realize that this is nothing but the truncation of f with kappa, the gradient of f minus kappa plus. Okay? And we are almost done. Perhaps I can finish the computation here. So now I just have to do 2 integrations by part, trying not to forget any minus sign. Okay? So I do 1 in V, 1 in W. So there is no sign. But when I do 1 in W, there is 1 hitting the minus W. So I've got minus the integral of 2 derivatives of A in V minus W. Okay? F mean kappa of W, F of V minus kappa plus dV dW. But as Maria explained, this is nothing but the Dirac mass with the minus. Let me put the minus with it. So this is nothing but the Dirac mass of V minus W. So what you end up with is a very simple quantity, which is the minimum of F of kappa V minus F of V minus kappa plus dV. But if you impose F to be greater than kappa, the minimum of F and kappa is exactly kappa. So you end up with integral of F minus kappa plus dV. So there is a very nice cancellation here. And what you end up with is a good truncated entropy estimate with which you can do the de Giorgi technique and get local regularity in time. This is what we did with Maria, François, and Alexis. Okay? So I call this term depleted term. And it allows you to give, to estimate, so partial regularity. Now Yann is going to complain. Partial regularity in time. Okay. But today there was local regularity. Oh, it's local in time, but it's not local in V. So I would like to explain next. I'm not going to do the full computation because you will get bored very quickly. And I will only explain how the computation we did before is changed. Okay, so perhaps I'm going to erase some parts. So this is a smaller break. Perhaps I want to keep this part. I'm improving, I think. Okay. I need to wait a little bit. So this is where we were. And yeah, I'm going to erase by hand this one so that if I write here, I think I won't be able to write anything else. So you want to localize those estimates. So the idea is rather simple, even if it took us a lot of time to find the right way to arrange terms. Okay, so you want d over dt, the integral of h of f. So this is the same choice. Okay, so I can emphasize that it depends on kappa, but I won't. And then you localize, for instance, in space, and you try to see what happens. Okay? With psi, for instance, equals 1 in a ball dr of v, and psi equals 0 in b of r plus delta v, v naught. So you localize around velocity v naught, okay, and like to see what happens. So the kind of things you obtain is the following. So basically, you have d over dt of h of f in the small ball. You will have to pay for the cutoff. The dissipation, thanks to the estimate by Laurent, I won't say much about that. You've got the square root of f, the gradient of square root of f dv. Also localized in this quantity. Okay, so this is very nice. This gives you a lot of integrability, a lot of information. This is very precious. And okay, so what is on the other side? You remember before it was just, let me write it again, kappa integral of f minus kappa plus. It was super nice, right? Here, it's a mess. What kind of a mess? So you are in the big ball first, and then you have a lot of error terms. So you've got the kappa that we had before. It is still there. Okay, at some point you put two derivatives on the side, so you have to pay 1 over delta square. That's life. Then you've got this guy divided by delta square. Okay. This is the factor. You've got the function f, okay, kappa f minus kappa plus. Okay. And then you've got the positive part of f over kappa. So this is reminiscent of this part, right? Log plus is only the positive part of the log. And if I want to be completely correct, I also have the square. Okay. So this is the local entropy estimate you have to work with in order to apply the Georgi techniques. So here, it is pretty clear that you need to do something with this guy, right? And the question is what to do. Okay, so I have 15 more minutes, even if, yeah, okay. So something I did not talk about, and it is very important in these de Gergy techniques, is scaling. Okay, so the Landau-Coulomb equation satisfies a two-parameter family of scaling. But here we are going to stick to only one. Okay, we are going to stick to this one, and we stick to this one because we want to preserve those estimates. And as a matter of fact, we should further reduce the type of scaling we are looking at. We need to consider the square here. Okay, so this works. And then I want to localize around a T naught V naught. So I do T naught plus epsilon square T and V naught plus epsilon V. So this is the kind of scaling you do. And when you do that, you do preserve the Landau equation, but you also preserve those estimates. When we did these estimates here comes from the lower bound we discussed before, that's C1 plus V square. Right, so you localize, so you don't care about the decay, but basically this is where it comes from. So you want to, you need to preserve this lower bound. So you need to preserve those quantities, and the only scaling you can work with is this one. So that's a formula, but if you, so at the beginning you work in a ball Q1 or anywhere. Okay, in the whole space, and what you do is that you localize. So this is time and velocity, and so you've got a time T naught and the velocity V naught. Okay, and so what you do is that you look at the equation in this very small cylinder. Okay, and somehow what you do, so I learned that from Alexis long time ago. So you zoom in, like on the iPad. He told me 10 years ago. Okay, and you're back to Q1. So this is basically the idea. Okay. Okay. So I would like to state the de Gergy lemma, the local one. So you see now, we forgot about the Landau-Coulomb equation. Okay, we trade it for the local truncated entropy estimates. Okay, we scaled, we kept them. And so the lemma is the following. So assume that this guy is bounded, okay, by a quantity that you can assume greater than 1, say. And also assume that the L infinity in time, LV, in the cylinder Q2. So you work here after scaling. Okay. Plus the gradient of F epsilon L2 square You also need to truncate it when f epsilon is greater than 1. So you assume that this is small. So the way you measure it is with this parameter compared to z epsilon to the 3/2. Okay, so I should put some color here. So remember, this guy can be very big, but the bigger it is, the more restrictive is the condition that I have to assume. So this is the condition. So there is an if. Then f epsilon is smaller than 2 in Q1. So now you're bounded, and so you're smooth. Okay. So this is the lemma. So basically, you have this inequality. Okay, and you want to prove at some point that some quantity is going to go to 0 in the spirit of the de Giorgi method I explained before. And so you need to do an iterative procedure that I don't have time to discuss, but you need to initiate it. And this is the ignition of the iteration procedure. And when you can initiate it, then you can derive the L infinity bound. Okay, so this was the end of local de Giorgi lemma. Now we already saw that, I did not explain, that we already saw, as explained pointed out by Luis, that in the axisymmetric case, so let me try to get organized for the last 5 minutes. So when you are axisymmetric, okay, you can take Z epsilon, basically something that is bounded, that is under control. Okay, but now you need to initiate the iterative procedure. You need to be able to prove that this is going to be small. As a matter of fact, when you are away from the axis, you get better integrability. Better integrability, it tells you basically that f is in L2 away from the axis. But the good thing is that if you're L2, then if you scale the L2 norm, it's going basically the L2 norm in this very small cylinder, so it goes to 0. And if you can control the L2 norm by applying the entropy inequality once, you can control this term and get this guy small. And if this guy is small, then you're smooth. Then you're done. Okay. As a concluding remark, we also studied partial regularity. Okay, so this has to do with the axisymmetric case. You can also try to see how big the set of singular points can be, and by using these estimates. And in that case, you don't have better integrability. So you need to do something to make this small. And we followed an idea by the proof by Alexis for partial regularity for Navier-Stokes. And we did what we call a linear iteration to make this small. But that's another story, and it's high time I stopped. Thank you very much.